In this presentation, we will discuss concepts related to performing a hypothesis test for the difference of two proportions. Note that this presentation is not meant to replace your reading of section 6.2.3 in the textbook. While watching this presentation, it would be very helpful if you follow along in the corresponding portion of the textbook. Lastly, please note that you're responsible for reproducing all parts of this presentation on paper according to our course guidelines for formatting of written work, except for any portions that appear in italics, which will occur starting on the next slide, or any slides within the presentation that are specifically identified as not requiring reproduction. Before watching this video, you should have a firm grasp of how to perform a hypothesis test for a sample proportion. This video is going to extend the methods from section 5.3, where we performed a hypothesis test for a single proportion, to apply hypothesis testing to differences of two population proportions. Note that in this course, we will only consider two proportion hypotheses tests when the null hypothesis is the difference of the two population proportions equal to 0, or equivalently, where we say that the two population proportions are equal to each other. We will use the information provided in section 6.2.3 regarding mammogram tests to walk through the four-step process to perform a hypothesis test for a difference of two population proportions. You will need to reproduce all work associated with the example, starting with the problem statement on the next slide. So on the screen, you can see I have gone ahead and copied the example regarding mammograms that was in section 6.2.3 of the textbook. I would ask that you pause the video for a couple of minutes, read the information carefully, and then we'll go ahead and proceed from there. Okay, so hopefully you've taken some time to read through the example. Going to the next slide, here's a question, and again, you don't need to copy this. This is in italics. If mammograms are much more effective than non-mammogram breast cancer exams, then we would expect to see additional deaths from breast cancer in the control group. On the other hand, if mammograms are not as effective as regular breast cancer exams, we would expect to see an increase in breast cancer deaths in the mammogram group. We will run a hypothesis test to see if there was a difference in breast cancer deaths in the mammogram and control groups. So we're going to use our familiar four-step process to perform the hypothesis test. The first step is the prepare step. We begin by identifying the parameter of interest. In this case, the example's parameter of interest is the difference in breast cancer death rates in the mammogram and control groups. Next, we list hypotheses. Those are given to us from Guided Practice 6.15 in the textbook, where we see that the null hypothesis has that the difference in population proportions is equal to 0, and the alternative hypothesis is that that same difference in proportions is not equal to 0. Next, we go ahead and identify the significance level. We're going to assume in this case that it is 5% or 5/100ths. The next thing we need to do is identify the sample proportion and sample size values for each sample and then use those to compute the point estimate. So we'll do that on this next slide. We see that the sample proportion for the women who died from cancer that had mammograms is 1,113 hundred thousandths when we do that calculation. And then we have the sample size of 44,925 people in that sample. For the sample proportion of women who died from cancer that had non-mammogram exams, we see that the sample proportion was 1,125 hundred thousandths, and the sample size was 44,910 women in that sample. We then go ahead and calculate the sample, the point estimate, the difference between those two sample proportions, and we get a point estimate of negative 12 hundred thousandths. The second step in our four-step process is the check step. We want to verify the conditions to ensure that the sampling distribution of the difference of sample proportions is nearly normal under the null hypothesis. So we first begin with the independence extended condition check. Because the patients were randomly placed into each group, they can be treated as independent both within and between the two groups, so that condition is satisfied. Next, we check the success-failure condition. When the null hypothesis is that the difference of population proportions is 0, we use a special proportion called the pooled proportion to check the success-failure condition. So the pooled proportion is defined as the number of successes divided by the total number of cases. So in this case, taking a look at that formula, we see that there were 500 women who died from breast cancer that had mammograms. We're going to add that to the number of women who died of breast cancer that had non-mammogram procedures, and then we're going to divide that by the total number of women in both of those samples. And when we do so, we come up with 112 10,000ths for our pooled proportion. So next we're going to go ahead and check the success failure condition using the pooled proportion value that we just calculated. So first we are going to find the number of successes, and we need to be a little careful. I've put successes in quotes because even though in the context of the problem success is what we're talking about, really we're referring to, it's a little bit of a morbid definition in this case because we're talking about success being somebody who died of breast cancer. So we just have to take that with it being in the context of this problem. So anyway, calculating that particular number of successes for women who had died of breast cancer but had mammograms, we find that there were 503 women that fall into that particular category. The number of successes for the control group, we take the pooled proportion times the sample size for that group of women, and we find that there were again 503 women that would then be identified as having died of breast cancer. The number of failures for those who were tested with mammograms, we see that there are 44,422 women approximately who did not die of breast cancer in that case. And then for the control group, we would find that the number of women who did not die of breast cancer in that case is 44,407. Now notice that in all of those cases, the success failure condition is indeed satisfied since all the values are at least 10. In fact, they're all much greater than 10. Therefore, with both conditions, the independence extended and the success failure conditions, with both of those satisfied, we can safely model the sampling distribution of the difference of sample proportions using a normal distribution under the null hypothesis. Moving on to the third step in our four-step process, the calculate step, we note that the conditions held during the check step. So now we can go ahead and compute the standard error using the pooled proportion. I've gone ahead and shown that now on the slide. You can see the formula for doing so. After running that through my calculator, I came up with the answer being 70 100,000ths for the standard error. The next thing we do is we compute the test statistic, capital Z. So I have that formula now shown on the screen, and I take the point estimate, which was negative 12 10,000ths. I subtract the null value of 0 from that. I divide that difference by the standard error, and when I do so, I get a value of negative 17 hundredths. Again, notice that we rounded that to 2 decimal places because Z values are always rounded to 2 decimal places. The next thing we're going to do is we're going to draw a null distribution sketch and identify the p-value. So we're now going to form a null distribution sketch, which we will use to identify the tail areas of interest for computing the p, or probability value. Notice that I start my sketch by putting the null value, that is the value from the null hypothesis, at the center, which was 0. I label my variable axis with the difference of sample proportions, and then the z-axis. The next thing I do is I scale my variable axis, going up by units of standard error. So remember our standard error was 7 10,000ths. So I go up 3 standard errors, and then I subtract that value from 0, going to the left, until I am 3 standard errors below the null value. Now that we have scaled our axis, we move on to going ahead and including some vertical lines going through plus and minus the absolute value of z on the sketch. So I've gone ahead and shown that. Even though I've shown these as dashed lines for illustration purposes, your sketch would have them as solid lines. And then I go ahead and I label those particular vertical line values, negative absolute value of z, positive absolute value of z. Remember to use the absolute value notation because in this case, that's important. We had a negative value for capital Z, so the absolute value helps keep this separated as being a negative and a positive value when we labeled it on our sketch. And then the next thing I'm going to do is I'm going to go ahead and I'm going to shade the tail areas that correspond to the P or probability value. And then we're going to go ahead and use RGuru to compute the P or probability value. And I've shown a sentence down below on the right that you would need to write on your paper to show the work for that being done on RGuru. I arrive at a probability or p-value of 8,650 10,000ths. And the last thing I'm going to do is identify that probability value by labeling the left-hand tail as half of that and the right-hand tail as the other half of that p or probability value. Now again, on the next slide here, closing out, I just want to remind you that I did not show how to use the RGuru calculator to find the p or probability value in this video, because I've done that before. However, again, do take note of how you would need to write on paper the work done using RGuru by including a sentence, just as I did on the previous slide. So the fourth step in our four-step process is the conclude step. In this step, we want to evaluate the hypothesis test by comparing the p or probability value to alpha, our significance level, and then we want to provide a conclusion in the context of the problem. So let's do the evaluation first. Because the p or probability value is much greater than alpha in this case, we are going to fail to reject the null hypothesis. So lastly, we now need to provide a conclusion. Therefore, the difference in breast cancer death rates is reasonably explained by chance, and we do not observe benefits or harm from mammograms relative to a regular breast exam. And that concludes this particular presentation.